Okay, think about this for a second. What if the next giant cloud data center wasn't built in some remote desert, but was launched into orbit? It sounds like science fiction, right? Well, today we're diving into one of the most ambitious, most audacious ideas in all of tech, moving the massive, power-hungry engine of artificial intelligence into outer space. So here's how we're going to break it all down. First, we'll look at the huge problem AI is creating right here on Earth. Then we'll explore the wild idea of solving it by going to space and the two brutal physics challenges that come with it, heat and radiation. And finally, we'll see who's actually building this future and what their roadmap looks like. All right, let's start with the why. Why are we even having this conversation? It all begins with a massive problem right here on the ground. You see, the incredible boom in AI is putting an unbelievable squeeze on our planet's resources. And when I say massive, I mean it. The scale is just mind-boggling. Some analysts are projecting that the market for AI compute infrastructure could hit $7 trillion by 2040. Now, that's not a typo. We're not talking about some niche little industry anymore. This is on track to become a foundational part of the entire global economy. But that kind of explosive growth has a cost. A big one. These AI workloads are incredibly power-hungry. We're talking about a potential 10-fold increase in energy demand for some data centers. That's pushing our power grids, our water supplies for cooling, and even the very land we build on to their absolute breaking points. So if the problem is basically Earth itself, our limited resources, what if the solution isn't on Earth at all? And that brings us to part two. Maybe we just need to look up for the answer. And this is the core idea, the big pitch. On Earth, our data centers are stuck. They're limited by the power grid, and they drink up insane amounts of fresh water just to stay cool. But in orbit, you get an all-you-can-eat buffet of free solar power. Your coolant is the literal vacuum of space, and you free up all that precious land down here. It's an incredibly elegant solution, at least on paper. Of course, it's never that simple, is it? Space isn't some friendly paradise. It's an incredibly hostile environment, and it has its own set of brutal rules. First up on the challenge list, getting rid of all that heat. And this right here is the fundamental problem. On Earth, if your computer gets hot, fans just blow air across it. Simple. But in the vacuum of space, there is no air. There's nothing to blow. So every single watt of heat that a GPU cranks out has to be physically moved to a radiator and then beamed out into the endless void as infrared light. If you can't do that perfectly, your billion-dollar AI chips will literally fry themselves. So that brings us to the absolute rock star metric for cooling in space, emissivity. You can think of it as a grade from 0 to 1 on how good a surface is at throwing heat away. The closer you are to 1, the better you are at cooling off. This single number is probably the most critical factor in designing radiators that actually work, and they're still light enough to get into orbit. This means engineers have a really tough trade-off to make. Do you go with the old, reliable, something like aluminum honeycomb? It's been used on the space station, it's tough, it works, but man, it is heavy. Or do you bet on the fancy new stuff like carbon-carbon composites? They're way lighter, but also way more expensive and complicated. For a big data center, that choice could mean saving hundreds of kilograms on launch day, and that's a huge deal. And just to make things even harder, if you're in low Earth orbit, space throws another punch. The thin atmosphere up there is full of these super reactive single oxygen atoms. This atomic oxygen is like a constant sandblaster, slowly eating away at the special coatings you need for high emissivity. Over time, it can literally degrade your ability to keep the whole system from overheating. Okay, so that's the heat. But space's second weapon is totally invisible. It's a constant, never-ending storm of high-energy cosmic radiation. And for modern electronics, it's absolutely lethal. Think about it. Modern AI chips are absolute marvels, with billions of microscopic transistors packed together. That makes them incredibly sensitive. A single particle from deep space can zip through that chip and flip a bit. A 1 becomes a 0. That sounds tiny, right? But that single event can corrupt an entire AI model or even cause the whole system to crash. And over time, that radiation just wears down the hardware until it fails completely. So how in the world do you protect these fragile little brains? Well, engineers are being incredibly clever about it, using a defense-in-depth strategy. It's a multi-layered approach. You start with special radiation-hardened chips. You add some targeted shielding, you build in redundancy so multiple systems can check each other's work, you even design the AI software to be tough enough to handle a few errors. And you wrap it all up by picking your orbit carefully to hide behind the Earth's natural magnetic shield. It's a full-on strategy. So, with these absolutely immense engineering challenges actually being solved, the big question becomes, who? Who is actually out there building this new frontier of computing in the cosmos? Well, first up, let's talk about Starcloud. This is a startup backed by none other than NVIDIA, and they've already made history. They launched a top-of-the-line H100 GPU into space, and get this, they successfully trained an AI model on it while in orbit. This is a massive it-can-be-done moment for the entire industry. And you know things are serious when the giants get involved. Google is in the race with something they're calling Project Suncatcher. They're not just thinking about it, they're already flying and testing their own custom, radiation-tolerant AI chips in orbit. When a player like Google puts its resources behind an idea like this, you know it's strategically important. And then you've got these super ambitious startups like Aetherflux. They're already planning their first commercial data center in orbit by 2027. But their vision goes way beyond that. They have a roadmap that scales all the way to massive interconnected constellations of computers, delivering just unbelievable amounts of processing power from space. And this new infrastructure? It's going to create a whole new economy. It's not just about moving servers. We're going to see space cloud providers, like an AWS for orbit. This will power things like real-time analysis of Earth for detecting wildfires or monitoring crops. It'll provide super secure computing for governments. It will even create a market for robots to go up and service or upgrade the hardware in space. Okay, so for our final section, let's look into the crystal ball a little. How is this future actually going to unfold over, say, the next 15 years or so? Believe it or not, we're in stage 1 right now. This is the era of demos and pilots, proving it can be done. But just look at how fast this thing accelerates. By the end of this decade, we hit stage 2, with early customers in defense and science. By the early 2030s, you could see large-scale constellations. And by the late 2030s, this is no longer some cool experiment. It's considered critical infrastructure, leading to a future where our entire global IT system is a seamless hybrid of computers on the ground and in space. So in the end, you can see this is about so much more than just faster chips or a neat way to solve a cooling problem. We are, right now, on the verge of building a permanent, powerful digital intelligence in orbit. And that leaves us with one last really big question to chew on. As we build this digital brain up in the heavens, what is that truly going to mean for our world right here on the ground?